Welcome to a lesson with Dr. Powell. Let's take a look at yet another way that we can do the problem of solving for or finding the work required to lift all the water in a conical tank. This time, let's develop the idea of the position, the height position of the centroid of this shape. So this is like a three-dimensional triangle, not a two-dimensional triangle. So it works a little bit differently in terms of computing where the centroid would land. It's not going to be 1/3 from the base. It's actually 1/4 from the base. Why is it 1/4? Let's use a little calculation. Okay, so for one thing, we need to kind of think about a variable here. Why don't we choose, why don't we think about our triangle situation again? Okay, something like this. And let's just think about rotating this around an axis, if you will. And so we think about a little change of volume is just going to be at a particular position X is just going to be kind of a little piece rotated around, a little slab here. And if we do that, we're going to get the cone overall. Okay, we keep on doing that, get that kind of a shape. So we think that the volume, and so why am I doing that? And that's because we need a little dm variable or a change of mass or change of volume, whatever, if you will, of this particular piece. So to do that, we're going to let our dm be the volume of this little piece of the cone, which would be the height of it is a little change in x and multiplied by the area of this. Well, let's give some specs here. Suppose this is okay, suppose this is radius, suppose this is h right here, okay, going like that. Then this function right here, take it as y is equal to r over hx, okay. So that would be, so pi r over hx, r over hx is the y value, which ends up being the radius, so square it right there. So that's your little change in m. Now, if we want to find the centroid of this, we find the average of this is like our dm. We take our x, because x is like the function we're finding the average value of, so it's x times your dm. But then you divide by the length of the mass interval, which would be the total mass, total volume, say, of this thing, which you could get by the volume of a cone, which is 1/3 height, or 1/3 base times height, which is 1/3 pi r squared h. And then we're going from, positions going from 0 to h here. Okay. Yeah. All right. I think that's right. Okay. So then, and here we end up getting, notice we'll have the r squared here will cancel with that r squared. So we can just kind of get rid of that. And h squared in the bottom is going to come out to be an h cubed over there. So the 3 is going to go to the top. This pi will actually cancel with that pi. Okay, so 3 to the top, and then we still have, but we can pull out kind of h cubed down there, going from 0 to h, and I pull everything out, so just have x squared dx, which will turn out to be 3 over h cubed times x cubed over 3 from 0 to h. Notice that we're going to plug in h and 0. It's basically just h cubed over 3. Those, let's see, is that right? Did I do it right? Oops. No. That's an x squared times x. Aha, caught myself. X cubed. X fourth. That looks a little bit better to me. Very good. Okay, then we plug the h in, and then we get, yes, that's right. We end up getting 3/4 times h, which is perfect. So 3/4 of the way this way, which would mean 1/4 that way. So 1/4 h is where it's always located for a cone. Now, you don't have to do this in general. This was just so we could establish the fact, and now free to use it. Okay, so This means in our cone example, we had 10 and we had 2. So what we're going to do is we're going to take the total force of the whole thing, the total weight, and we're going to be moving this total weight over a particular distance. And why don't we think about this as being focused in at a point? This whole mass, right, is focused. That's what centroids do. Centroids simplify integrations because actually they allow you to be able to pretend that everything is pinpointed at a particular location. So this total mass, so the total force, is pinpointed right there. And then to move position-wise, we're just moving a constant force from here up that far. So 1/4 of the way. So the total distance to travel is 1/4 of 10, which is 2.5. So we have 2.5 feet to travel for the entire volume. So the entire volume is going to be 1/3 base, which is pi times 2 squared, times height, which is 10, times, and then we should get 2.5. Oh, but wait a minute. We also need to put something else in. We need to put in 62.3 in order to get the total volume. Yes, in order to get the total volume. Okay, I mean, force, to get the full force. So we multiply this to the volume to get force, because this is pounds per cubic foot. This is cubic feet. The cubic feet cancel. This is force. So you get that force multiplied by your how far you're traveling. And that should be the work. So let's check that. So we get 40. So we get, so this is 40 over 3, and right, which is the same thing as 100/3 if we multiply by 2.5. What I'm thinking for that is I'm kind of in my mind going like 0.25 times 10. I'm just kind of rewriting 2.5 is 0.25 times 10. And then I know this is, and then that 0.25 will cancel with that 4. And I just have 100/3. So that's what I'm thinking. 100 pi over 3 times 62.3. And let's compare that to what we had. I guess I could have simplified what we had before. Yes, could have simplified very nicely. Aha, yeah. So where we ended before was 2,500 over 75 times 62.3 pi. And notice that 25 over 75. So that'd be like, this is like 1/3 times 100, but that's like 100. So this part right here is actually 100/3. Hey, so wow. All we did was just this one little calculation, and we got the total work without doing any integration at all, because the integration was actually already done for us in the centroid. Now, if you remember centroid facts, then you remembered a lot of integration in hand, and you can just apply it very quickly. So for a cone, it's only 1/4 of the way in order to get the centroid point. Thanks for watching.